Welcome to the second video in our series. In the first video, we looked at lightweight residential construction to see how it would behave and react under fire conditions. In this video, we burned down an old warehouse. We got an old warehouse downtown, about 6,000 square feet, masonry, heavy construction, sort of typical old downtown looking building. We wanted to test how old heavyweight construction would behave under fire conditions. NIST helped us again, and on this test they actually used a little bit more sophisticated CO reading measurement equipment. We wanted to take a look at what the survivability for unprotected occupants curve would look like as far as time frames and the degree of CO. And we also wanted to establish the time frames for safe offensive operations as far as our firefighters were concerned. So we used the test kind of for both of those things. These type of buildings are very, very typical in downtown areas, in older areas of the city. As I mentioned, this building is over 50 years old, kind of a classic old heavy construction building as far as the roof assembly is concerned, masonry walls. They have large floor areas. When under fire conditions, they hold up for a while, and you can see that in this, but when they start coming down, they come down quick, and it's pretty spectacular when they do that. So we wanted to just see how that was going to behave as far as the time frames are concerned, and you're going to see it here on this video.
A key ingredient in the firefighter safety equation is the ongoing evaluation and reevaluation of the incident's critical factors. The culmination of these factors equates into what strategy and position firefighting forces will be operating in. This will either be offensive interior positions or defensive exterior positions. The timely and ongoing analysis of these factors keeps the incident action plan current and firefighters safe. The decision to commit firefighters to interior attack positions in burning buildings must be based on a deliberate, conscious, and realistic size-up. In most cases, this size-up is made in seconds during the worst possible time when the building is on fire. These split-second decisions have been traditionally made based on the experience of the initial arriving officer. There isn't much hard science that examines the evolution of a structure fire. In an effort to take a more scientific look at the way buildings hold up and react under fire conditions, the Phoenix Fire Department has partnered again with the National Institute of Standards and Technology, known as NIST, for a second set of burns that focused on old warehouse-type construction. A 1950s-era warehouse that was slated for demolition was donated for the project. As with the residential burns, the main focus of these burns was to determine collapse times and the window of opportunity for conducting safe roof operations. Another area of focus on this set of burns was to examine the interior conditions of the building during the burn, looking at temperature and carbon monoxide readings and how they related to the survivability profile of unprotected occupants and the safety of interior crews that would be operating inside the structure. The building was outfitted with equipment that measured temperature and carbon monoxide concentrations. It was then set on fire and burned down in the name of science and firefighter safety. The goal of the project is to collect data as it pertains to the survivability of the interior and attempt to match fire conditions with the imminent collapse of the structure. The building was a single-story warehouse that measured 135 feet by 50 feet for a total square footage of 6,750 square feet. The building was divided and burned in two separate sections. The front half of the building was 90 feet long and 50 feet wide. The back half of the building was 45 feet long and 50 feet wide. The two halves of the building were separated by a 2x4 wall covered with 1/2-inch OSB. The OSB was then covered with 2 layers of 5/8-inch fire-rated gypsum board. The structure was built of red brick with lime mortar. The front half of the building contained a small set of rooms that served as offices and restrooms. This front portion of the building had an acoustic tile ceiling that was attached to 2-inch by 8-inch purlins. The purlins were on 2-foot centers and secured to the bottom chord of the roof trusses. The roof system. The building had a peaked roof made of large dimension lumber. The top and bottom chords of the trusses were made of 2x12s. The web members were made of 2x8s and 2x6s. The trusses were on 15-foot centers and rested on the bearing walls. Many of the trusses had been reinforced with metal cables and were supported with 4-inch diameter steel columns. The trusses were covered with 2x8 sheeting to form the roof deck, which was covered with felt and 2 layers of asphalt rolled roofing. The structure was 18 feet high from the peak of the roof to the floor. The large front section of the building was the first to be burned. 3 arrays of thermocouples were evenly spaced throughout the 90-foot section of the building. Each array of thermocouples began at the roof peak and ended at the floor. Temperature readings were recorded at 12 incremental positions between the roof peak and the floor. Carbon monoxide readings were taken during each of the research burns. Samples were taken at 2 different heights, 1 inch and 3 feet from the floor in each scenario. The metering equipment was placed in the center section of each of the burn areas. The big half of the building was the first to be burned. The building was vacant and empty. 3 stacks of 10 pallets each were put in the northwest corner of the building. A single stack of 10 pallets was put 15 feet from the rear wall of the burn area. It is important to note that other than the building itself, there was no other fire loading in the building. The pallets were set on fire using newspaper ignited by an electronically controlled book of matches. All recorded times started when the book of matches was ignited.
2, 1. We have ignition.
It's important to note that no flammable liquids or any other accelerants were used for these tests. "40 seconds after ignition, flames reached the tops of the pallets. Flames reached the top of the ceiling and started to spread laterally 90 seconds after ignition, and smoke was visible from a rooftop ventilator. At the 2-minute mark, temperature readings showed only slight increases. The temperature at the ceiling level was 286 degrees. At floor level, the temperature was 102 degrees. All 3 stacks of pallets were well involved in fire at the 2-minute mark. 2.5 minutes into the test, the radiant heat from the pallets started to ignite adjacent items in the structure, and temperature readings started to rise dramatically. The fire extended into the attic, and fire became visible from a rooftop ventilator 3 minutes after ignition. Temperatures were 1,242 degrees at the ceiling and over 1,300 degrees at the 6-foot level. The floor level temperature was nearly 200 degrees. Carbon monoxide readings remained at a 0% concentration. At the 4-minute mark, approximately 15% of the roof was involved in fire. Interior temperatures were 1,144 degrees at the ceiling, 1,118 degrees at the 6-foot level, and over 600 degrees at floor level. Carbon monoxide levels started to rise at the 4-minute mark to 600 parts per million, but were below the lethal concentration of 5,000 parts per million. Also at the 4-minute mark, smoke was banked down to floor level, and there was 0 visibility in the interior of the building. At this time, the cool cams recording interior conditions were pulled to prevent them from being damaged. At the 4-minute mark, a size-up of the conditions when viewed from the exterior would indicate a defensive fire attack. 5 minutes after ignition, the fire started to become oxygen-starved, and smoke and heat production started to diminish. Temperature readings fell, and carbon monoxide readings rose drastically. The ceiling temperature went to 662 degrees, and at floor level, it was 369 degrees. Carbon monoxide levels at 3 feet went from just 600 parts per million at the 4-minute mark to 19,400 parts per million at the 5-minute mark. This reading is almost 4 times the lethal dose of carbon monoxide. At this point into the burn, any non-protected occupant in the interior would be overcome and killed by the products of combustion. At the 6-minute mark, the burn interior temperatures fell again to 486 degrees at ceiling level and 360 degrees at the 6-foot level, while the carbon monoxide level almost doubled to 34,800 parts per million, well beyond lethal levels. 7 minutes into the burn, temperature and carbon monoxide levels remained approximately the same. The exterior fires on the roof were in an oxygen-starved, smoldering condition. At the 8-minute mark into the burn, 10 minutes prior to roof collapse, The front two glass doors were broken out on the end of the structure to simulate the entry of first arriving fire crews. Interior temperatures and carbon monoxide readings remained stable, and there were blackout conditions inside the building. The ceiling temperature was 452 degrees, and the carbon monoxide level was 30,100 parts per million. The carbon monoxide level remained well over the lethal limits for the rest of the burn. At the 10-minute mark, 2 minutes after the doors were removed, various fires reignited on the roof, and interior temperatures started to rise again. The ceiling temperature on the interior rose above 700 degrees. Fire vented through the northwest corner of the roof 11 minutes after ignition, and data indicates the BTU production versus water application would be overwhelming, and extinguishment at this point would be highly unlikely. There was a minor interior collapse at the 11-minute mark, which probably caused interference with the metering equipment. All interior temperature readings remained the same at all three measuring levels. Carbon monoxide readings remained above the lethal dose limits. At the 12-minute mark, it is safe to assume that roof operations would not be advised, as the roof would be unsafe. Approximately 25% of the roof was involved in fire, and the interior fire was ventilating through the center of the roof. 13 minutes into the fire, data transmission from the monitoring equipment was lost, possibly due to another collapse on the interior of the building and direct fire impingement on the metering equipment. The front quarter of the roof was well involved at the 14-minute mark, and interior conditions would have to be considered fully involved. A large portion of the roof suffered a catastrophic collapse 18 minutes after ignition. This is 2 minutes short of the fire-ground 20-minute rule that is applied throughout the fire service today. As stated earlier, the interior of the fire building was only fire-loaded with 40 pallets. It's speculated that any heavier fire loading or volatile material fire loading would shorten the collapse time for the structure. 19 minutes and 30 seconds after ignition, a portion of the front wall collapsed into the street. 23 minutes into the fire, most of the remaining roof collapsed. Shortly after the collapse, the fire was extinguished with ladder pipes to prevent damage to the firewall separating the two units. Flames reached the tops of the pallets 45 seconds after ignition. The entire array of pallets were fully involved 2.5 minutes after ignition. Between the 3 to 4 minute mark, flames were spreading laterally across the bottom of the roof deck. Temperatures at the ceiling rose from 410 degrees to 1,389 degrees, while the temperatures at the floor rose from 77 degrees to 112 degrees. The CO readings were at 0%. 5 minutes after the initial ignition, smoke was banked down to the floor, creating total blackout conditions on the interior of the structure. At the 5-minute point, interior temperatures ranged from 1,200 degrees at the ceiling level to 321 degrees at the floor. The CO readings at the floor rose to 1,235 parts per million. Fire started venting out of the open roll-up door at the 6-minute mark, and the CO reading at floor level was 6,800 parts per million. 7 minutes into the burn, the interior temperatures ranged from 1,030 degrees at the ceiling to 725 degrees at the floor. The CO reading at both the floor and 3-foot level were over 42,000 parts per million, 8 times the lethal dose for carbon monoxide. At the 8-minute mark, the CO metering equipment failed. 9 minutes after ignition, the fire was burning between the junction where the roof met the parapet walls. Between 13 and 14 minutes, the recording devices failed and the roll-up door collapsed. The roof had a partial collapse 15 minutes and 20 seconds after ignition. The roof was mostly destroyed 19 minutes and 30 seconds after ignition. The rear wall collapsed 29 minutes into the event. The fire had basically burned itself out 7 minutes before the collapse occurred. The biggest difference between the two burns was the available oxygen. Burn 1 took place in a tightly sealed building. By the 5-minute mark in burn number 1, the fire had consumed most of the available oxygen and started to diminish. By 8 minutes into the first burn, the ceiling temperatures had dropped from a high of almost 1,200 to 452 degrees. The two glass doors were then broken out and the fire rapidly took off. 4 minutes after removal of the doors, approximately 25% of the roof was well involved in fire. The actions taken at the 8-minute point in burn number 1 are probably realistic, if not optimistic, of our arrival time to the scene. It's very important to note that the roof collapsed 10 minutes after the doors were removed. In contrast, the second burn had a large overhead door, which remained open during the test. The fire never lacked for fresh air. Temperature readings at the ceiling level between the 3-minute mark and the 13-minute point, where the recording devices failed, remained between 800 and 1400 degrees. Peak temperatures and CO readings were similar for both tests. The interior camera was pulled at the 4-minute mark in burn number 1 because the smoke was banked to the floor. In burn number 2, the camera was pulled at the 5-minute mark for the same reason. By the 5-minute mark, total blackout conditions existed on the interior of the structure during both burns. At this point, if you're not wearing and using an SCBA, you're starting to die because the CO levels are becoming lethal. If you're not on a hose line or have a thermal imaging camera, you're lost in the heavy smoke. The maximum temperatures recorded prior to collapse in both tests was 1,470 degrees. The peak CO readings for both burns were over 40,000 parts per million. The highest recorded CO readings occurred between the 6- and 7-minute mark in both burns. CO readings reached lethal levels by the 6-minute point in both burns. During the first 6 minutes, burn number 1 had a peak temperature at the floor of 610 degrees. Burn number 2 had a peak floor temperature of 463 degrees. 6 minutes into both burns, any unprotected occupants would have been dead from either the high CO levels or the elevated temperatures. The instruments used to collect the data stopped working between the 13 and 14-minute mark in both of the tests. We suspect the building was starting to come apart, and that caused the instrumentation to fail. The roof in burn number 1 had suffered a collapse 18 minutes and 20 seconds into the fire. 23 minutes into the fire, the remainder of the roof came down. The roof in burn number 2 had a partial collapse 15 minutes and 20 seconds after ignition. That roof was almost totally destroyed by fire 19 minutes into the test. After the test fires exhausted their fuel supplies and burned themselves out, the building continued to fall apart. Sections of wall fell over well after the fire was out. This reinforces the safety policy of staying out of the structure's collapse zones. The active fire load was calculated for the burn in the small end of the structure. Based on the fuel content contained in the 30 pallets and active fire involvement of 50% of the roof system, the heat production was approximately 1,700,000 BTUs. This amount of heat was generated during the first 7 minutes of the fire. Since 1 gallon of water absorbs 1,700 BTUs, it would take 1,000 gallons of effective water application to extinguish the fire. It would take over 5 attack lines flowing directly onto the burning fuel to accomplish this. For all practical purposes, this information is merely interesting. If we plug our normal response into the recorded readings and burn timeline, entry and tenability into the structure wouldn't have been possible beyond the 5-minute mark because of the elevated temperatures recorded from the floor to the roof. This was the case for both burns. 13 minutes into both tests, the structure was falling apart. The instrumentation placed inside the structure showed us that all unprotected occupants inside this building would have perished by the 6-minute mark. The structure started to come apart by the 13-minute mark in both burns. This was indicated by the instruments failing due to collapses occurring inside the structure. In both burns, the structure suffered catastrophic collapse well before the 20-minute mark. A final note. The intent of these tests were not meant to come up with final solutions and absolutes on how we're going to conduct operations at fires in these types of buildings. They were conducted to give us a more scientific look at how these buildings burn and to apply that information to some degree while operating on large commercial structures.